everyone, and thank you for joining us today for our AIA certified webinar, Cracking the Code NFPA 285 Wall Assemblies. My name is Rachel Hunt, and I will be the moderator for today's presentation. Before we dive into introductions, I'd like to go over a few logistics. First, we're working remotely, so if we run into any technical difficulties, we will pause the presentation for up to 5 minutes to allow us to try and troubleshoot. If we can't, we will cancel today's presentation and reschedule for a later time. We will send out an email communication with new details if needed. Next, we will conclude the webinar with a live Q&A session. So if you have any questions throughout the presentation, you may submit them via the Q&A box on the right side of your screen. If you don't see the Q&A box on the right side of your screen, simply click on the Q&A in the top right corner and that will open a dialog box that you can use to submit your question. A quick note before we get started, this webinar is for educational purposes only, and it should not be used as a substitute for professional engineer designing, consultation, or documentation that may be required by building codes, contracts, or applicable by law. If you have any questions after this webinar, you can refer to our specific application guidelines and instructions located in the product sections of our website. Additionally, we will follow the webinar today with a survey, and this is your opportunity to provide us with feedback on how we did today and ask any additional questions that you might have about the topic. And you also have the opportunity to suggest new topics for future webinars. This survey is also part of how we deliver the JM experience to you. And the JM experience is based on the 4 pillars of JM culture, which is listed on the bottom left corner of the slide: people, passion, perform, and protect. And we believe it's critical to make sure that we hear, understand, and respond to your needs in order to deliver the best interaction for you. We offer webinars like this one to help educate the market and to offer a tool and resource for you and your business. But we understand that this isn't just a one-way street. Your feedback is a key component to helping us evolve to better meet your needs. So if you have any comments or suggestions as how we can better accomplish this, or even if you feel like we've missed the mark today, we encourage you to fill out the survey. We use your feedback to improve our webinars and provide the information that we have that's most valuable to you in future webinars. Also, we're frequently asked about if we're going to send this presentation upon the conclusion. While we don't send the presentation itself, we do post a webinar recording online, which you can share and view at your leisure. And this ensures that the presentation is presented within its full context. This will be sent via email to you once it's live on our website. So with that, I will hand it over to Jeff Job.
Thanks, Rachel. Hopefully everyone can hear me. This is Jeff Job with Johns Manville, Senior Specifier Services Representative for our Building Insulation Group. Focus mainly on really technical support for not only our sales team, but also the design and architecture community. So really that resides around code compliance, details, questions about product performance, applications, conditions, kind of all those things that go into how the products can be used, limitations, etc. My contact information is there on the screen. Feel free to reach out to me directly if you do have any questions, as well as we will show some resources for other ways to contact JM later in the presentation as well. Other than that, I would just say a lot of my background, I've been with JM about 6 years. Most of it's really in project management. So I did project management for a construction company prior to that. So contract administration, kind of all things related to that. So that's where a lot of my background is. And, this kind of topic is kind of near and dear to my heart, in that it's, something that we ran up against, in the field of having, of course, submittals, proving compliance for code approvals, all that kind of stuff. So with that said, let's go ahead and get cracking here. Fine print slide for everyone. Not going to read through this in painstaking detail, other than to point out, of course, the course is approved for a 1 LUHSW credit hour through AIA, and the course is copyrighted property of JM. And we will, of course, submit your attendance to AIA on your behalf. Learning objectives and the agenda for today are going to be touch a little bit kind of just on the emphasis of testing, you know, maybe some of the examples of things that we don't want to have happen to us in the built environment, and lead that into a little bit of the history of the kind of how the testing, where NFPA 285 evolved out of, and then really focus mainly on kind of the actual conducting of the test, as well as kind of what that looks like after the fact, right? Kind of what documentation do we have? How do we make that available? And help you guys kind of interpret that to then, you know, build a compliant wall system on your end. So with that said, let's go ahead and kick things off into the emphasis on testing. Now, really what we're seeing here, of course, is examples of fires that are burning on the exterior of, in this case, high-rise structures. And this is, you know, without kind of jumping ahead of myself, but these are kind of exactly the kind of issues that the NFPA 285 test is trying to, of course, deter, right? So these are things we don't want to happen, obviously, and that's, you know, kind of, I think, thankfully, we haven't seen any, you know, examples to this scale in the U.S. And a credit to, you know, NFPA 285 and building code for, you know, having fairly, you know, stringent requirements here in the U.S. That photo there in the middle, that was, you know, that structure in China was actually under construction at the time, so there was no, you know, deaths in that one, even though that looks like a, you know, almost a complete loss. You know, some fairly highly publicized examples there in Dubai that I think most people have probably seen, you know, on and off from the news over the course of the last few years. And then, of course, you know, this one here really kind of being, you know, the epitome, if you will, of what we're trying to avoid here, the Grenfell Tower disaster that occurred in 2017. Without going into tons of detail behind this project, it was essentially kind of a renovation reskin. They put a metal panel assembly on there with a Polyiso insulation in behind it. And of course, fire broke out inside a unit, which led to fire propagation throughout the entire structure and a significant loss of life here. Over 70 people died. Lots of other issues related to, you know, egress restrictions, issues with the building that, again, I'm not going to get into, but of course, exactly the kind of, you know, tragedies that, you know, we're really trying to avoid when we're talking about the introduction of combustible materials in non-combustible building types, which is kind of the overarching theme of the presentation and where NFPA kind of 285 comes into play here. So with that in mind, kind of the testing origins of where all this kind of was born out of was really through the plastics industry and the introduction of Eaves in the U.S. Back in the 70s, you know, we had the oil embargo, kind of some energy struggles in the U.S. You know, how we're, you know, where are we getting our energy from? How are we using it? And a couple of things kind of became abundantly clear when the government looked at some of the bigger pictures. Was that one thing? Buildings were extremely inefficient, and that was kind of a huge wake-up call. It's like, oh my gosh, we're just dumping tons of energy into these structures, are consuming vast amounts of energy. You know, we need to start improving that, and that's really where kind of the, you know, the energy code push, you know, was instigated, and obviously where we see it today with, you know, iterations fairly often, and even some, you know, fairly stringent ones as of late, related to envelope performance, air change requirements, etc. But one of the kind of the first material systems that came out to try and address this, well, that was really kind of, you know, fairly heavily publicized, was the Eaves system, which is essentially a synthetic stucco. I like to think most of the people on the call are at least, you know, mildly familiar with it. Very lightweight kind of version of stucco. It's, you know, it's essentially, you know, a mastic acrylic based type system versus an actual masonry type system. You know, ideally it works very good. I think we've kind of figured out a lot of the issues with it. You know, it's a waterproof, it's got insulation built on the exterior. Of course, one of the key components of that insulation being it's usually EPS or XPS polystyrene product, which of course is highly flammable. So with that in mind, just another quick kind of breakdown on Eaves systems here if you're not familiar with them. Again, basically an adhered synthetic stucco system over, you know, your fairly traditional kind of water resistive barrier system there. Lightweight, energy efficient, you know, lots of different kind of textures and options available today. But really that's kind of where the introduction of Eaves and the understanding that, my gosh, this is a, you know, a pretty effective system, but it is also extremely flammable, right? So really kind of understanding what we need to do to understand that the flame propagation within those systems, as well as really understanding how combustible they are, maybe, what are the kind of the limitations here of how big can we go, how tall can we go, things like that. And really kind of the first test methods that were developed is UBC 26-4, otherwise known as standard methods of test of fire resistance of building construction materials. It was a 2-story full-scale fire test. And I will, there is kind of a distinction there between your full-scale 2-story versus your intermediate scale, which is what NFPA 285 is, and I'll explain that here in a second. This test really looking specifically at combustible components, I should say the combustible components being essentially EPS, polystyrene, really was the main focus of this particular testing. It was first acknowledged in the UBC building code back in 1988. And what you see here again, full-scale test, meaning in this case, full-scale meaning you're mocking up literally a full-scale model of a building. So the full wall system, the structure, everything at a minimum of 2 stories, and we're essentially kind of burning that to the ground, and then taking a bunch of measurements along the way to understand how this flame's spreading, how fast it's spreading, how hot the structure is getting, etc. Again, kind of specifics to this test, it was really focused on analyzing how an interior fire can affect, exterior flame propagation via that, the exterior facade of that assembly, knowing that, in an Eaves type application, we have some fairly highly combustible materials in that system. It was added as an actual specific reference to UBC in 1997. And then kind of the test that we know today, NFPA 285 standard, was rolled out in 1998. And that one was now developed as a much more repeatable test, less costly in that we're not having to build the entire full structure, 2 stories, everything every time. And it was really designed to test, applies to all combustible materials, right? We're not specifically just looking at Eaves, namely, the polyiso or the polystyrene portion of it. We're really trying to set up a repeatable method where we can measure flame spread via the exterior wall assembly of all potential combustible materials that we might be using in the exterior of a wall assembly. Now, why do we want to maybe use combustible materials in the exterior of a wall assembly? Well, a lot of it's kind of driven by energy code in that as codes kind of, each iteration, they get adopted within the US. I got a quick kind of snapshot from the Division of Department of Energy here, showing kind of code adoption, energy code adoption in the US, kind of, just where we're at nationally. But again, as these codes get adopted, a lot of them have, increased requirements for continuous insulation, which of course has, been a fairly hot topic over the last probably, at least 10 years, and continues to still be a hot topic as, as these codes get adopted. It kind of gets harder and harder to make a code compliant wall assembly that's not incorporating some level of continuous insulation. So it could be continuous insulation, it could be building wraps, it could be other materials. Oftentimes these synthetic combustible materials are the ones that have very good energy performance properties. They have very good thermal performance, they have good air barrier properties, they can act as a vapor retarder or as a water barrier. So there's a whole slew of products available on the market that are very highly performing, and it so happens from they tend to be rated as combustible per code. CI, as I just kind of alluded to here, tends I think to be the one that most often comes to mind, and really here just kind of laying out the most common use of foam combustible plastics that we see in the exterior wall assemblies. Of course, your rigid foam board products, your ISOs and your polystyrenes. Closed cell spray foam is another option that we see increased usage on the exterior. Could be of course Eaves systems where this kind of was born out of structural concrete forms or insulated concrete forms, structural insulated panels, etc. Are these other types of wall systems that generally are trying to incorporate some level of continuous insulation, and most times it's some type of combustible foam product. Mineral wool, of course, we have on there, which is non-combustible. That, of course, ties into this conversation. We're going to kind of skip that for now, but we will bring mineral wool back up later on, as really now we want to focus mainly on those combustible materials in those wall systems. And kind of where this tends to come to a head, if you will, or kind of a confluence, for lack of a better term, is when we have energy code and then we have building code. We just kind of discussed some of the overarching concepts and desires behind energy code. Energy efficiency, use of continuous insulation, higher performance building wraps, etc. Well, building code, on the other hand, is oftentimes when we're talking about large high-rise structures, buildings that have a significant amount of occupancy, it's more driven towards, means of egress. And that's, of course, built into any structure. And what's driving that is essentially the height of the building, the floor area of the structure, as well as the use and occupancy classification of that building. So simply put, buildings that are taller, buildings that have more floor area, buildings that have, more occupants, or maybe occupants that are, mobily restricted for one reason or another, they need to essentially last longer in the event of a fire. They need to, of course, all buildings need to provide that means of egress, but based on those three factors is going to kind of dictate the fire resistance stringency, if you will, of how long that structure kind of needs to stay intact to allow those people to evacuate the building in the event of a fire. And of course, that kind of leads us to the 5 building types that we see called out here. And those 5 building types are, buildings are classified into one of these 5 types based on those three determining factors we just looked at. And we kind of see the continuum of combustible to non-combustible called out here, starting, of course, at the top with combustible. That is our type 5 construction, where really those are buildings that don't take very long to evacuate. Generally, they're 1 story. They're not housing, a significant amount of people, and thus code allows them to be built out of combustible materials because it doesn't take them long to be evacuated if they do happen to catch fire. The type 1 through 4 structures, though, as you see listed out here, are calling for, at a bare minimum, non-combustible exterior walls, or a fully non-combustible structure if we're really getting into some of those tighter, stringent requirements, high-rise structures, large assembly halls, things like that. That are going to dictate, a fully non-combustible structure. So any one of those, any structure that falls in those types 1 through 4, the non-combustible requirements, whether it be just exterior walls or fully non-combustible structure, are now kind of up against energy code, and that we just, energy code's kind of driving us or kind of prodding us to use these combustible materials in our wall systems to make them more efficient. But building codes are now saying, hey, wait a second here. You're in a type 1 through 4 structure, you can't do that, right? Or we need to at least maybe set some boundaries. And that's kind of where the whole, NFPA 285 comes into play, right? And it's when we're introducing these combustible materials into type 1 through 4 structures that dictate non-combustible exterior wall materials, if not fully non-combustible structures. The 3 most common, I would call it trigger points, if you will, are what we're calling out here on the right, where we most often see the introduction of combustible materials in an exterior wall assembly. Could be your air and water barriers, which was included into IBC back in 2012, as far as having now those materials being subject to NFPA 285 testing. Combustible claddings you see listed there, the various kind of years they were adopted into code as far as now being the trigger points for NFPA 285. Eaves, composite metal panels, fiber reinforced panels, high pressure laminates, et cetera. And then of course, foam plastics we're calling out there at the bottom, which have really kind of been in there from inception, whether it be Eaves or your Polyisos, your CIs, that's kind of where this whole test was born out of. So they've kind of always been subject to it. Couple of exceptions I'm kind of calling out there on the left. The exceptions were pretty important, I would say, maybe just a few years ago, and I'll explain kind of why that is. And I would say they're less important now. And we'll get to that in a second here, but some of the kind of exceptions related to water resistant barriers, if it's of course a structure that's 40 feet or lower, you're going to have an exception. That's not going to be a requirement. I can see various kind of height restrictions that are related to some of the combustible claddings. Of course, all structures incorporating foam plastics, except for 1-story buildings with sprinklers. So if it's maybe a 1-story building without sprinklers, you still might be subject to NFPA 285. And one other thing I'd mention here is we're not specifically kind of addressing that, but the cavity insulation, right? So if that cavity insulation is a combustible material, that would also be a trigger point for NFPA 285. So in the absence of any one of these, if you have a combustible component kind of anywhere in that continuum, that's likely going to trigger the need for compliance if that structure is considered a type 1 through 4 classification. Couple other things to kind of mention here. Again, a whole bunch of kind of slew of exceptions that came out in code in 2015. That was kind of a bit of a pushback to the introduction of WRBs in the 2012 code. I'm not going to go into these in kind of painstaking detail. namely because almost all of them just got rescinded in the 2021 IBC. So there was kind of a handful of exceptions that got put in related to WRBs mainly. Just some pushback there related to height, the actual kind of embodied energy in that material, et cetera. But in the latest version of IBC, the 2021 code basically rescinded all of the kind of the most common exceptions that were out there. So as that code begins to get adopted throughout the US, kind of your ability to, I don't want to say skirt, but maybe, find an exception to NFPA 285s getting smaller and smaller. So it's going to become more difficult to avoid having to meet compliance of this test. One other thing I do want to mention that is a common question we get all the time related to NFPA 285 is that kind of in relation to fire resistance ratings, otherwise kind of known of as your hourly ratings of assemblies, our UL 263s, our ASTM E119 testing, which is measuring essentially how long a particular structure is going to resist flame spread, resist temperature rise over a period of time, right? So, we have our building types listed there horizontally at the top of this scale. This is, of course, right out of building code. So we have our types 1 through 5, and we also have, various hourly ratings that these particular wall systems or structural systems need to adhere to based on the building type that we're falling into. Now, the point of mentioning this is these hourly ratings are separate from NFPA 265. So NFPA 265, as we'll get to here in a second, is strictly measuring flame spread via exterior wall systems when we're dealing with combustible materials. Now, of course, UL 263, there's tons and tons of testing out there. All types of wall systems, roof ceiling, floor ceiling assemblies, roof systems, et cetera. It could be a lot of different things, and they're not analogous with one another. And that's a question we get oftentimes is, hey, I have a 2-hour rating on this wall assembly. Does that mean it also is going to meet UL 260, or excuse me, NFPA 285, or vice versa? This wall system is 285 compliant. Does that mean I don't have to prove compliance with the hourly ratings you see here? And the answer is they are not synonymous. They are not analogous. They are not interchangeable. You often, it could be a situation where you need to prove compliance or show testing that proves compliance for both requirements. So with that said, let's kind of get into the meat of the actual test itself. The latest version is the 2019 version, a standard fire test method for evaluation of fire propagation characteristics of exterior wall assemblies containing combustible components. So it's kind of broadened its scope a little bit over the years, and now that the latest version also contains, it allows for testing of both load-bearing as well as non-load bearing. And it's really looking at combustible components in exterior wall systems, not limited specifically to the initial tests that were just those foam plastics. We're really trying to understand, develop a repeatable test that's applicable to any use of combustible material in an exterior wall assembly. Again, kind of just calling out some of the versions out there. Again, the latest version 2019, there was a 2006 version as well, but these seem to be the ones that kind of had some prominent changes that I think, the industry had to take notice of. And especially here on the last one that we'll kind of talk a little bit more about, and we're calling it there at the bottom of the final bullet, updates to joint and seam locations and window header construction. Now, we'll get to that here in one second, kind of what that means in terms of the latest version of that test. So these are kind of some snapshots right out of the manual, and just kind of pointing out some of the base requirements of what that wall assembly looks like. Now, one distinction that I want to make here, and I'm actually going to jump to the next slide, which has all the same bullet points on it, but just a different, now we're kind of looking at a cross section here versus a plan view, or excuse me, an elevation view of what we saw before. Now, so this test is considered what was referred to as an intermediate scale versus the full scale test that we had previously, which was literally a full building out of the entire structure, wall assembly, floor, ceiling, etc. And now in this case, this test is what referred to again as an intermediate scale test, where now we're just basically mocking up that wall assembly, which is otherwise referred to in the parlance of the test as the test specimen. And we have what is essentially a full concrete non-combustible structure, otherwise known as the test apparatus, which is a permanent concrete structure that these wall assemblies are then mounted to. So this allows for the cost of the test to come down significantly to really allow manufacturers to test more combinations of assemblies. but again, it's essentially a wall assembly being mounted to the test apparatus, and then from there we will see how a fire is exposed to this test specimen. Minimum requirements for the wall are 13.4 inches wide, 13 feet 4 inches wide, 17 feet 6 inches high. It must include a window opening. It must include a horizontal joint that extends the full width of the wall assembly, as well as now a vertical joint that runs the full height from the window opening up to the top of that wall assembly. So that was a new addition to the 2019 test, and quite frankly, it makes the test more difficult to pass. It's now considered more stringent in that those joints, those connections, oftentimes tend to be kind of weak spots in the wall assembly, and now that is a requirement for anything that's tested since 2019 moving forward. You do have to incorporate that full vertical joint. So test measures really two things. It's going to measure both flame spread via that exterior wall assembly as well as temperature rise. So there's a whole bunch of thermocouples, otherwise known as thermometers, that are placed within the actual test apparatus. So within those two rooms, right? So we're kind of simulating a two-room mock-up here. We have, think of a high-rise structure. You have, units stacked on top of one another. There's thermocouples placed inside those rooms, as well as within the actual test specimen itself within that wall assembly. And of course, they're measuring temperature rise. There's different requirements for the temperature of the wall assembly versus the ones that are placed in the room. But again, there's over 50 thermocouples placed throughout the test assembly when it's all set up. I'm not going to call out every single one or show you all the details of where they're placed, but just kind of give you an idea of what that looks like and kind of what it looks like here in the actual test phase. You have all those thermocouples linked up and set into that monitoring system there. So really what we're measuring is, or what we're trying to simulate is, again, that flame that's, occurs inside, the interior of a multi-story unit. That fire then kind of flashes over, breaks through that exterior window, and is now being exposed to that exterior wall assembly, and really understanding how that flame is going to move through that wall assembly. So there's two burners that take place, and the initial one starts, when the test initiates, it runs for 30 minutes. The first set of burners is that interior burner that is lit in the first story. There's, again, simulating a fire in that lower unit. That burner runs for 5 minutes, and then we fire up the window burner you see there on the left, exposing directly to the exterior wall assembly. The temperature increases every 5 minutes until we hit that 30-minute cap, and then the burners are shut off. So again, trying to simulate this fire is getting more intense. It's getting hotter as it consumes, more of the structure. Again, trying to be as real life as possible in this simulation. So that test runs for 30 minutes as those burners go, and then again, what we're trying to measure here is flame spread through that exterior wall assembly, both vertical and horizontal. So a passing test from a flame spread standpoint is the flame cannot extend greater than 10 feet above that rough opening, or 5 feet horizontally on either side of that rough opening. And flames cannot occur at all in the second story of that mock-up we see there. It also measures internal flame spread, so flames cannot extend vertically or horizontally into that wall cavity. They must stay within predetermined temperatures, namely they cannot exceed 500 degrees. So any thermocouple in the interior spaces cannot exceed 500 degrees. Any thermocouple in the actual wall assembly itself cannot exceed 1,000 degrees. And of course, flames cannot occur beyond sidewalls of test apparatus. So those are kind of the base parameters of what would consider a pass-fail. If you're, just outside those parameters, it is considered a fail. You've burned your wall assembly. You spend a bunch of time, energy, and money, and now, you might be back at square one if you didn't pass. Hopefully, if you pass, you get to move on and kind of go from there. Before we kind of get into what some of the documentation that we look at when after we pass a test, and just go through some examples here of some stock images of what this kind of looks like, right, and explain a little bit more about it. So just some base images here of a test that was mocked up. This is a metal panel assembly that was burned. In this case here, I'm kind of calling out that vertical joint you see there with the circles and the arrows. You can see the flame being exposed to the wall assembly, and then kind of what that generally looks like afterwards when the wall's actually burned. One other thing to point out, and this was we get a lot of questions about this too, so I wanted to kind of bring this up in the presentation, is related to the header, the jam seal header requirements of that window opening, right? And so per the test requirements, it's supposed to be, I shouldn't say it's supposed to be, test dictates metal aluminum plate that encompasses all sides of that window opening, really there to try and simulate kind of an aluminum window frame that is then, the flame has broken through and is now, flashing over, is now impinging on, burning on that system. No materials could be used to fill the air gap cavities, if any, or further cap the header jams and the sill areas. So per the standard requirements of the test, you can't put any fire retardant materials in there, FRT wood or, mineral wool blocking, things like that. That's not allowed. You basically just have to cap it as you see here, and then run the test. Now they do allow for, you see that last bullet there, client's unique construction details may be used but must be adhered to during real life construction. So if a manufacturer wants to deviate from kind of the base requirements you see here per the standard of this window opening, they're certainly allowed to do so, but then they need to be very explicit about that detail of that construction in their documentation of, okay, yes, we passed the test with said assembly, but we deviated from the standard opening and we did this, this, and this. And now in order to maintain compliance with that manufacturer's testing, you would need to follow those same details, on your job site. So just something to be aware of there. It's not uncommon for manufacturers to deviate from the standard. But again, I think any reputable manufacturer is going to be pretty explicit about, what they did to deviate. And of course it is, you're required to outline what you did in your deviation, and then that deviation needs to be adhered to in the actual construction of the, real life construction if you're moving forward with that manufacturer in that particular assembly. So just things to be aware of there, something to keep in mind. So now we've got a quick little video I'm going to show you guys of kind of what this test looks like in action. A nice video produced via Lever Building Materials here, and I'm going to jump to my desktop real quick, and we'll watch this briefly here, and give you guys an idea what this kind of looks like in action. Okay, hopefully that came over relatively well and kind of give you guys an idea of what that looks like. So with that said, say, we burned a wall, it passed. What does that kind of, what does that look like on, on our end, on the user's end? How do we make that information available, communicate that to the design community? So once the test is completed, we do receive a, fairly lengthy, complicated document that is our test results. From there, we generally, most manufacturers, I would say this is a fairly common process, is going to work with an outside engineering firm to kind of distill down that information, summarize it, if you will, make it available to the general public in the form of an ESR, otherwise known as an evaluation service report. You can think of ESRs, if you're not familiar with them, as kind of an executive summary of code compliance for that material. So ESRs oftentimes include all types of information, not just specific to NFPA 285. It's usually a whole bunch of really good information, kind of summarized how that product is compliant per building code. Essentially, it's kind of an executive summary of what limitations, detailing, et cetera, that might be required to use that product in relation to various codes you need to comply with, both residential and commercial. And what that oftentimes, I also mention here too, usually it's kind of a summarized table, which we'll look at here in a second. Common ESR providers, ICC, IAPMO, Intertech, Dr. J, I'm sure there's more out there. I would say those are probably 4 of the biggest ones that are being used by the industry. If you're ever looking for compliance information, I would highly suggest either starting with your manufacturer's website I would think if they've done any testing, they're going to have that available to you, or you can go directly to the websites of those organizations you see there, search them either by product name or by manufacturer name, and if they've done testing with that group of that material or that manufacturer, it's pretty easy to find that information on their websites. But again, I would think manufacturers' websites probably the best place to start. And kind of the easiest way I think we trying to make this available is in what you see here, what I kind of refer to. It's basically a table of all the combinations of assemblies, right? And it's kind of a choose your own adventure wall assembly build out is kind of the best way to think of it. You walk down the table, you select the various components, and therefore assuming all those components tie out with ones you want to use on your job site or want to use on your project, then you can meet a find compliance within this table. So with that said, I'm going to kind of walk through it to give you guys a better idea. I think people oftentimes see these kind of individual tables might be made available specifically in that form on manufacturers' websites as well. They're not always embedded in an ESR, although you do often see them in ESRs if they have done that type of testing. Base wall system. So kind of first course of our direction here on our path to compliance. Pick one of these 3 options. This is just an example of one kind of table we have to show you guys here. So in this case, there's one of 3 options available: concrete wall, concrete masonry wall, so CMU, otherwise steel stud options you see there. So start there, we pick one of those. Okay, we'll say we're using steel stud, great, now we're gonna move on. In this particular case, mineral wool, friction fit, floor line fire stopping is required, friction fit in the wall system in this case. So we would need to provide that in this particular option. That's kind of mandatory. There's no deviating from that. Cavity insulation. So again, do we want any insulation in our wall system? Maybe, maybe not. If we're doing continuous insulation, maybe we don't. All kind of your most common materials you see listed there are available in this case. Your fiberglasses, your mineral wools, even potential for spray foam combinations as well. So we picked our structure. We picked whether or not we want continuous insulation. With our exterior sheathing options, if we're doing concrete or precast or a CMU wall, we might not need any exterior sheathing. Or traditional kind of steel frame construction, we're probably going to need to pick either 1/2 inch or 5/8 type as JIP, which is what's called out there in options 2 and 3. What's our WRB, right? So again, lots of different options here. Manufacturers may have umpteen, various options. You can see here a number of options. In this case, you might see many more, less. Just depends on what the manufacturer has done, who they've tested with. We'll kind of explain a little bit more later on how kind of we determine what's available in these various options. Exterior insulation. Are we putting any exterior insulation? Are we putting any CI in the wall system? Yes, maybe we are. In this case, we can go up to 3.5 inches. Maybe if we look at the note below, if we're doing some of our more robust claddings, if it's CMU, brick, something like that, we might be able to get away with a thicker foam insulation. So again, I would say most manufacturers are well within this range of 3.5, 4 inches, etc. Rarely are we putting that much as CI on our exterior wall systems, kind of per what energy codes generally requiring. So, you can pretty comfortably say that you can go up to the maximum thickness, in this case called out, of 3.5 inches. So 3.5 inches or less is compliant within any of the materials we've picked thus far, and with any of these cladding materials that you see listed here. So again, this is probably the area of greatest competition amongst manufacturers is A lot of those base components are fairly well defined. It's more of, what kind of claddings can we get approved in our systems here again, and I'm not going to read through every one of these in painstaking detail, but again, you can see you kind of got your, your bricks, your brick, your stucco, your masonry systems, all the way down to, fiber cement panels, in this case, solid metal, a plate aluminum cladding is available in this option as well. So again, that's kind of how these tables work. You can pick any combination of the options you see there are going to be compliant per whatever that manufacturer's testing has provided them. Some of the things to consider, right, are of course coordination with multiple manufacturers in the specification, right? We just looked at, of those various combinations there, it could be anywhere from, you're going to have at least probably eight different manufacturers of the various components and potentially more depending on compatibility, et cetera. And, they all need to be part of that approved assembly, right? And I think that's kind of the key from a compliance standpoint and from a, proving it to a code official, right? Is you just need to make sure, it's really, critical kind of in the pre-construction phase to say, okay, we know we need to meet this compliance. We've gone through, we've selected an assembly that is compliant for whatever manufacturer, we decided to use. And then, making sure that you're communicating that with the suppliers. Obviously, a lot of them that have quote unquote combustible materials are familiar with this and probably, can help guide you along the way as well. And then making sure those are the materials that are actually getting built in the project, right, or getting installed in the project, because that's what's going to ultimately determine if you're compliant or not. You can have everything on paper, but if that's not what gets installed, kind of harkening back to the Grenfell Tower, they started off with good intentions, and there was a various number of kind of value engineering options that led them down the path of non-compliance. Regardless, that's a whole separate kind of testing environment in the UK. But again, kind of be cognizant of that's a potential path you could follow here that you don't want to, that would lead you to compliant at one point, and then all of a sudden what's getting installed not compliant. So making sure you're understanding if there's mock-ups or pre-construction meetings that need to take place to really understand that, as well as substitution requests, right? That can start becoming a little more complicated as well. And do we even want to deviate from the test in the first place, right? So maybe it's a new product on the market that we really want to use, no one's tested it yet, or it's for whatever cost purposes or number of different reasons, right? We've got an assembly that we like, everything's compliant, but one or two things we want to tweak. That's kind of going down the engineering judgment route. So manufacturers have done tons and tons of testing to try and make their products as applicable as possible. Now, if we want to kind of deviate from that, then it's kind of on the design team to take the next step of going through the engineering judgment process to determine whether or not said material that they want to use that is outside of options of compatibility can be used in a test. And that's basically bring out a third-party engineer to test the material. And really what they're looking at is mainly how combustible is that material in relation to what we're trying to substitute it for, right? So if it's a WRB or if it's a continuous insulation, is the material we want to use that's not listed as combustible or less combustible, more fire resistant than the one that's already listed? And if it is, then that's a fairly clear path for the consulting engineer to move forward and say, yes, we are going to sign off on this, and this is an allowable material in this assembly. And that's really kind of boils down to the cone calorimeter test. That's really the test that's kind of measuring the embodied fuel, if you will, inside that of that material. So that's kind of you can see kind of the various benchmarks they often use in relation to making that decision. But that kind of tends to be the big one, right? It's all based on we're not considered about is it airtight now, or is it going to maintain my WRB, my drainage plane. They're specifically looking at fire performance, combustibility in relation to whatever material we're considering exchanging it for. Fire performance, is different amongst materials, and I think we kind of alluded to some of this a little bit already. But just to kind of give you, I guess more of a broader understanding from the concept of what's available on the market currently from NFPA 285 approvals, right? So think of it maybe of your color palette of claddings, that are available based on the materials I want to use. So of course, fiberglass mineral materials, are non-combustible, right? So essentially no restrictions there, right? Mineral wool's, becoming more and more popular as a continuous insulation because it is non-combustible and it helps kind of, eliminate some of the headache related to meeting compliance of NFPA 285. Now, for example, if we put mineral wool in a system that also had a combustible metal cladding or some other type of combustible cladding, you're still subject to NFPA 285. You're not, you can't just eliminate one and then have another trigger point and you're good to go. You really need to, and there's tons of testing out there with metal panels and mineral wool CI insulation in behind that. So just things to be aware of there. It can be, eliminating one trigger point is not necessarily your silver bullet, but it can definitely kind of be one option of taking, that component out of play from compliance. Now your thermoset materials, your polyisos, your closed cell spray foams, it's a different chemical bond than your polystyrenes. It's more structurally stable in the event of a fire. It will char. It stays structurally intact. It will not melt away. So you're going to find the next tier, if you will, from an insulation standpoint, your continuous insulation standpoint is going to be with your polyisos, your foil faced, closed cell foams as well. Very broad array of approvals there. You're going to find metal panel approvals, of course, fiber cement. Metal panel was kind of, I'll call it the unicorn approval there for a while, and that it was a very difficult system to get past. We've seen quite a few, past assemblies over the last couple of years, and I would say that's becoming less and less of a challenge to find NFPA 285 compliant systems that are including metal panel. So you will find metal panel approvals with your polyisos. Thermosets, your polystyrenes, which of course kind of harkens back to Eaves systems, et cetera, they are still far and away, the least effective from a fire standpoint. They are the most flammable, and therefore you're going to find the least amount of approvals on the market, right? So if you're using polystyrene, EPS, XPS as your CI, that's going to be, you're going to be the most limited from your cladding standpoint. You're going to be pretty much limited to stucco, your brick, your masonry, your type of veneers, that kind of thing. So again, just kind of keeping in mind, material selection is going to, make your life, easier or more difficult depending on kind of where you're going and what you have to do from a code compliance standpoint. So kind of wrapping things up here, just to kind of follow up on some of the highlights of the things we just discussed. Moving forward, nearly all construction in the U.S. is going to it's going to be really hard to kind of avoid NFPA 280 compliance moving forward with where ASHRAE, IECC, energy code requirements are going, or where they kind of currently are, depending on where you're at in the country, with the requirements, for air barriers. All your kind of, fluid applied, liquid applied WRBs are going to fall into this. Of course, continuous insulation, your foam products. It's going to become more and more difficult to kind of, find exceptions or avoid compliance with NFPA 285 moving forward. Of course, it's required when we're using a non-combustible material in all type 1 through 4 non-combustible required structures. Measuring flame thread through exterior wall assemblies not equivalent or kind of a substitute for our fire resistance ratings, our UL 263 or ASTM E119. Just want to reiterate that because that is a common question that comes up. Looking to manufacturers' literature to find and understand compliance, reporting, what's available. And I would say specifically too, don't feel free to reach out to us, reach out to the manufacturers. I mean, we're there to kind of facilitate, the use and understanding and applicability of our products. And if you don't feel like you have to kind of do this in a vacuum, by all means, contact us directly. We're happy to help kind of interpret our information for you if you're struggling to understand, nuances related to kind of that, that table that we looked at. And then of course, coordination of all manufacturers, we discussed this already as well, can be a challenge related to just the sheer number of available options out there when we're thinking of exterior wall assemblies, between WRBs and continuous insulation and the claddings. I mean, it is endless, and I don't envy your guys' position in having to make some of those decisions, and that there's a lot of options out there. But again, I would just stress to lean on your manufacturers to help you navigate this process. So this concludes the educational portion of the presentation. With that in mind, we want to just kind of touch on some JM resources specifically available to you, and then we will wrap up here shortly and answer as many questions as we can in the allotted time. So of course, one thing we did want to bring to your attention in relation to NFPA 285 is some new available cladding options with our kind of, I want to say, workhorse, if you will, in the exterior wall assembly foam segment here, our AP foil continuous insulation, the Polyiso product there. You can see, what the claddings we had available in the past, and with some recent testing and approvals and everything kind of I's dotted, T crossed information available to the public. We've been able to pick up some new claddings. They're autoclave aerated concrete, thin brick, fiber cement board, fiber cement panels, as well as solid metal plate panels there. So again, kind of just making you guys aware that we do have some additional options, cladding options available with that product line, and really I think now closing some gaps that we did have with this, but it is widely available and a good option for pretty much any type of kind of material you want to use now. With that said, I'm going to turn it back over to Rachel to kind of wrap us up here and then move into the question portion and answer portion of the presentation.
Thanks, Jeff. So before we get into the questions, I do want to go over a few resources that we have available. First, as I mentioned earlier, this webinar has been recorded and we'll be posting it on our website under the source. And this is where we keep all of our installation intel resources, which include additional webinars, blogs, trainings, document resources, and more. This is a great educational tool that you can access from the JM Building Installation homepage. Next, I wanted to mention that we are on LinkedIn and Twitter. So on LinkedIn, that's your opportunity to stay up to date on everything going on in our commercial and residential channels, which include upcoming events, product announcements, available resources, and more. And we're also on Twitter at Installation Intel, or you can use the hashtag Installation Intel. And this is an opportunity for you to get all the latest in installation. We share and post the industry trends, insights, and educational opportunities for all types of installation. Next, I wanted to highlight our specifier service team, which is part of a team of experts that we call Tech Connect. Jeff is a member, as well as Dwight Stone and Jerry Fox, and they assist with questions, code specifications, substitution requests, available products. They provide educational presentations and more. So if you ever have any additional questions or need support, please contact the specifier service team through this email or phone number listed. I'll leave this slide up while we answer questions so you guys could jot it down. And then finally, I wanted to highlight the certificate of completion. So everyone who attended today will receive a certificate of completion in their inbox by this Friday. And if you submitted your AIA number when you registered, we will submit your certificate to AIA for you to earn credit. But if you did not submit it, you're welcome to self-support using the certificate of completion that we will be sending. So with that, we'll move over to some questions, and we'll go a little bit over the hour. So if you guys aren't able to stick around, go ahead and send me a message, and if you asked a question that we didn't get to, we'll follow up separately. So joining Jeff is Dwight Stone, and he is a building enclosure specialist at JM. We will begin with some of the pre-submitted questions and then move on to questions submitted during the presentation. So to kick off, I'm going to ask, how does the JM Polyiso system differ from those used on Grenfell Tower in the UK?
Yeah, so simply put, what was used on the Grenfell Tower was a Polyiso cyanurate foam board product. JM's products are Polyiso cyanurate foam board, and as we saw, they're kind of the upper tier of fire performance when we're talking about rigid foam boards compared to polystyrene. But the critical kind of, without getting into total weeds on Grenfell Tower, the main critical feature was the MCM panel. It was actually an ACM panel, aluminum composite panel that was used. Did not have a fire-rated core and was essentially not really allowed to be used over 18 meter on structures over 18 meters high in the United Kingdom. Of course, that structure is much higher than 18 meters. So it was kind of a litany of, again, oversight, value engineering, kind of other issues related to the airspace in the structure. Kind of, there was a lot of questioning about the air gap that was allowed between the foam and the metal panel. So that system would have never have passed an NFPA 285 assembly test. So those would be kind of just some of the basics of the fatal error there in the Grenfell Tower. Really was more to do with the cladding than it was kind of anything else.
Great, thanks, Jeff. All right, next question is, what, if anything, needs to be submitted for a permit package to satisfy NFPA 285 compliant?
Well, I mean, I don't think there's any kind of one standard, way to go about it here. Again, I think it's kind of just depends on, I would, quite frankly, I would, rely on the ESR, rely on that information, the table, provide a highlighted map of here's the materials we're using, here's how they're compliant per this testing, and bottle up all the product information of the various manufacturers that are tied to that. I mean, that would kind of be my process of going about it. Again, I don't think we don't have any kind of standardized documentation to submit other than relying on those ESRs. And then if you need to get a manufacturer involved, kind of maybe help spell it out for, the code officials or things like that. Again, we're kind of happy to do that. I don't know if you have anything to add there, Dwight.
Sure. Hi, everyone. Yeah, the only thing I would add is that in the specifications, just make sure that you are correct in terms of needing an NFPA 285 assembly. So that's the first question. Then you don't want to exclude good products out there, especially in a tight insulation environment that we currently have, unnecessarily. But then if that is already determined and you've used a chart or manufacturer's assembly, one of the tested assembly charts out there, simply print a copy of that chart and include it in your submittal if required by the entity.
Thank you. All right, next question is, with so many air barrier materials, insulation materials, and different configurations of these products for a wall assembly, what would be the most important logical way for a designer to approach the design of an NFPA 285 compliant assembly for buildings greater than 4 floors?
Well, I mean, I think we kind of covered that. That was, at least I hope that was definitely part of the intent of the presentation, was at least, it's relying on the manufacturer information, those ESRs, those tables, and kind of, walking through that table step by step. That's really, I would think, the easiest way to kind of narrow down, or maybe even starting the bottom up, right? It's, hey, here's my cladding. Do we need CI? Maybe we don't. Okay, then we can kind of, rule out that particular component, et cetera. I think those choose your own adventure tables, as I like to refer to them, are probably at least the most useful thing available to the industry at this time. One other thing I'd mentioned related to that, I know I kind of threw out some of the testing agencies and manufacturers' websites. There is no kind of one-stop shop repository of NFPA 285 information available, unfortunately. So there isn't kind of one centralized database where you can plug in a manufacturer or material and kind of get a list of options. It's you kind of need to settle on a manufacturer or a system and kind of work within that, and then maybe you have to deviate from that, maybe you don't, but just relying on those tables and the various options within them, I think, is probably the most kind of clear-cut way to go about it.
Great, thanks, Jeff. Okay, I might mess up this last name, but how does this relate to Joe Listbrook's perfect wall?
Yeah, so it's pronounced Steebrook, Rachel, for the unindoctrinated.
Thank you.
Nonetheless, so Joe's perfect wall, right? If I'm not mistaken, it's essentially the key component of the perfect wall is the insulation and the weather control layers are outboard of the structure. So I think kind of cladding, independent of the cladding, that's kind of his key, right? Is we move the insulation out, we move the air and water control layers out, and we allow the structure to stay kind of, minimal thermal fluctuation, dry, et cetera. And that's kind of the basis of the perfect wall. It's essentially insulation that's outboard of the structure. I think that's exactly where Energy Code is trying to steer everything, in that, there's a lot of information out there, Joe Steebrook being one of them, of, hey, really trying to push the point home of exterior insulation is a more efficient system. It's definitely way more efficient than kind of doing your traditional, stud cavity insulation, especially if you're using, metal studs, things like that. So, I think the industry is really, trying to, steering more towards quote unquote the perfect wall. And, that's, case in point with some of the systems we showed here, and where a lot of this testing is going is that more and more, insulation is going in the exterior in the form of continuous insulation. And, really just trying to, again, make it as kind of as easier, as easy for the designers to understand and utilize from a manufacturer standpoint as we can. I don't know if you have anything to add there on that one, Dwight.
I'm familiarizing myself with the perfect wall as we speak, so nothing yet.
Okay, great. Next question is, can you describe the field testing requirements and laboratory testing requirements?
I mean, I would say really from a field testing requirement standpoint, there isn't any. I mean, it's, we've tested this in a lab. We have this documentation that says these combination of materials assemblies are compliant. As long as you're kind of staying within, the boundaries of that, then there is no field testing that needs to be done. Again, if it's a situation where it's a one-off, or it's a system that doesn't have, or you're trying to get a material that doesn't have any compliance reporting available, or moving the way of an engineering judgment, something like that would be an option. Or in some cases they're doing specific wall system testing for individual projects that that does occur. But from an actual field testing standpoint, there really is no on-site requirement, other than I would say a mock-up would be a great way to kind of again walk through with the code official. Here's the mock-up of exactly what we're doing. Here's our materials. Here's how they meet compliance per this combination of approval. This options here, and that would essentially to me be the kind of the field, the step in the field that would need to be potentially proven.
Yeah, I agree on that. The field testing is something you definitely would not want to ascribe to an NFPA 285 test. Field mock-ups, definitely important for, and they could be in situ mock-ups, definitely important for constructability and construction quality of the assembly, confirming that. And maybe something the official would want to look at before you close things in. But the field testing, I would leave more for water testing and acoustical testing to determine effective acoustical ratings. But lab testing, if this is, I guess this is technically lab testing, is very important for confirming the 285 assembly will pass the fire test. Yeah, field testing, unfortunately, is what is happening on the buildings that have not been that have had issues with their fire, and that's something we would definitely not want to ascribe to the 285 test.
Thank you. The next question is, what temperature is the test performed at?
Well, I don't know the set temperatures of those burners, other than to say, we kind of showed that table in there of how essentially the BTUs are increased each time every 5 minutes over the course of the 30-minute period. And then, the thermocouple thresholds are, again, 500 degrees for the interior thermocouples, and then 1,000 degrees of the ones that are placed on the actual wall assembly. So in any event, if you're exceeding those temperatures, whether it be inside the room or in the wall assembly, that would constitute a fail per the test.
Okay. The next question is, oh, sorry, go ahead, Dwight.
Yeah, the limits that I'm aware of are 500 on some of the exterior thermometers or thermocouples, and 1,000 for others. So there's a map if you're interested in going into the weeds on that in the NFPA 285 test requirements.
Great, thank you. The next question is there an index listing of tested assemblies that include the specific component, so someone can determine if there's a matching assembly or not?
I mean, again, I think, we're back to, those tables that we showed, right? And oftentimes they're included in the ESRs, which are great resources that explain a lot more about code compliance than just NFPA 285. But I think, again, that's oftentimes included in a manufacturer's ESR if they have one. You will find individual kind of tables available, on manufacturer websites. That tends to kind of be what the most common method for listing available options. If it's a specific cladding or something like that that might have very specific details, and oftentimes that'll be included. And that's just something else to be aware of. Again, if it's there might be based on the robustness of the assembly or the cladding, we can kind of fairly well assume that our masonries and our concretes, claddings are going to pass the assembly. But if it's a nuanced metal panel or some kind of other material that's doesn't have a lot of testing behind it, there might be some very specific details, again back to that idea of maybe deviating from the wall assembly per the testing. Just something to be aware of there, that there may be some specific details tied to a said manufacturer's approvals.
Great, thank you. So the next question is, are there products available that are less based on fossil fuel? The person who asked brought up traditional heavy stucco and new materials like carbon sink materials, such as wood pulp or other organic material. And I'll probably pass this one off to Dwight to answer.
Thank you, Rachel. So from my understanding of carbon sink materials, those would include cellulose materials, and in terms of an insulation product. And then on exteriors, I'm really fairly unfamiliar of cellulose-based cladding materials that would be used in a 285 test, especially since you're introducing cellulose into a fire test. You're going to have some difficulty passing with those assemblies. But continuing with carbon neutral materials, or I guess carbon absorbing materials, titanium dioxide is a coating you can actually apply over some MCM panels. So you may want to look in terms of that type of material. It definitely would not be inexpensive as an application, but does have carbon absorption characteristics. But in terms of plastics, they're all based on MDI and polyol, so they're all oil-based products. If you want to get away from oil-based materials, you're going to basically eliminate the need for the NFPA 285 test, because then you end up with the fibrous materials like fiberglass and mineral wool.
Great, thanks, Dwight. And we're almost to 10 after the hour, so this will be our last question. If we did not get to your question during the live Q&A, we'll follow up separately. So the last question is, NFPA 285 test apparatus looks similar to the edge of slab floor-to-floor test. To what extent are they related, and can they be performed at the same time?
So from my understanding, the slab floor-to-floor test is about fire going around the edge of slab. So that they are, although they have similar characteristics in terms of fire translation from floor to floor, they're completely different tests. It's a very interesting question. I'm sure technically you could do the measurements at the same time, but they are completely different tests for basically fire propagation between rooms and in assemblies.
Great. Thank you so much, Dwight and Jeff, for your time today. And as I mentioned, if we didn't get to your question, we will be following up with you directly. And also mentioned earlier, if you submitted your AIA certification number, we will report this learning credit for you. And if not, you can submit the completion certificate that you will receive on Friday for submittal. Thank you everybody for joining us today, and we hope that you found our webinar informational, and we will be sending an email with the recording as soon as it's live on the website. Have a great rest of your week.